Alright, in this video I'm going to go over section 4.7, which is L'Hopital's rule. I'm just going to do a bunch of examples that essentially demonstrate the method, and I'll go through kind of different tiers of the problem. They kind of get more and more difficult as we go along. So let's look at a couple examples here. So here, faced with any limit, L'Hopital's rule says if you plug in the value of which I'm approaching and say, so if we plug in the value 0, we're kind of assuming that the function is continuous there, but it doesn't really have to be. So if you plug it in, I'm clearly going to get 3 times sine of 0 up top, and on the bottom I'll get 5 times 0. So sine of 0 is 0, so I get 0 over 0. So this is what's known as a indeterminate form. And it's kind of the most basic type of indeterminate form. So it's called indeterminate because a lot of times if limits, after you plug in the value, if it comes out to be 0 over 0, the limit could actually be anything. It could be 0, it could be infinity, it could be 5, right? It doesn't matter. So that's why it's indeterminate. We're not sure what it could be. L'Hopital's rule says, okay, if I'm in that type of indeterminate form, the limit as x approaches 0 of this function divided by this function is actually equivalent, assuming this next limit exists, of the limit of the two derivatives. So I take the derivative of sine of 4x, which I'll do that down here. So the derivative of that would be cosine of 4x times 4 because of the chain rule. So this is 4 cosine of 4x. So plugging that in upstairs, we would get this. And on the bottom, derivative of 5x is 5. Now, if this limit exists, then it is equivalent to the limit here. So we, again, assume the limit, the function is continuous there. I have 12 times cosine of 4x over 5. If I plug in 0, we see that this function is continuous at 0. So I get 12 times cosine of 0 over 5. Cosine of 0 is 1. So my answer is 12/5. So this limit is 12/5. Okay, so this is kind of the most basic type of L'Hopital's rule in the sense that this is the most basic indeterminate form. So getting a little bit more difficult here, if I go towards infinity, right now the limit as x goes to infinity of this function, we notice that this would be e to the 0 because 1 over x approaches 0 as x approaches infinity. So we get e to the 0 minus 1, and again 1 over x, the function, so I'm looking at this as the bottom function. This approaches 0 as x goes to infinity. So I get 1 minus 1 over 0, which is 0 over 0. So again, I'm in this, this indeterminate form here. So what I've written here in brackets is essentially just to demonstrate what happens when I plug in, well, as I approach infinity in this case. I get that indeterminate form. So now I can do L'Hopital's rule, which essentially states, all right, do the derivative of the top and the derivative of the bottom. So e to the 1 over x, we have to do that derivative, so that's kind of a difficult one. So the derivative of e to anything is just, again, e to that same thing, but now I have to multiply by the derivative of 1 over x. And again, this is the chain rule, so we have e to the 1 over x times, let's see, I'll write this as e to the negative 1, right, prime of that, so this would be negative x to the negative 2, so we get e to the 1 over x negative times 1 over x squared. So that's my derivative in the top. So it would be negative e to the 1 over x times 1 over x squared, and then the derivative of minus 1 is 0. And here we just did the derivative of 1 over x, it's negative 1 over x squared. Okay, so before I try to plug in infinity or approach infinity and evaluate this limit, it's best to algebraically, right, simplify this thing. So in the top I have, right, let's see, negative e to the negative to the 1 over x. The 0 just kind of goes away, and then I have times 1 over x squared. And in the bottom I also have a negative 1 over x squared. So I hope you guys can see that, right, these negatives cancel and these 1 over x squareds cancel. Right? so they're just gone. So we have the limit, right, as x approaches infinity, of just e to the 1 over x. And again, as x goes to infinity, the exponent goes to 0. And so my answer here, right, is 1. So this original limit is equal to 1. So L'Hopital's rule says, right, if the limit of the derivatives exists, then the original limit is equivalent to that. Since this exists, it's equivalent. Okay, so those were 0 over 0, both of those problems. So let's try something else. So in this problem I don't have a ratio of two functions or a quotient, right? What I have is a function here multiplied by another function here. But we can still go with this idea, right? If I plug in 0 plus, which is essentially just 0, I will get sine of 0, right, times, and then this is 1 minus 0, and this is going towards 0 plus as well. So sine of 0 is 0, and what do I get here? Well, this is essentially the square root of 1 over 0 plus. Can't really divide by 0, but as x approaches 0 plus, this thing would go towards infinity. Right, so I actually have what's called an indeterminate product here. So we can't use L'Hopital's rule directly because I still have a product of two functions. But this is called an indeterminate product because, right, this still could be anything. It's very similar to the 0 over 0 or infinity. You might think, oh, 0 times infinity should be 0 because 0 times anything is 0. But infinity doesn't really abide by the laws of algebra, right, because it's not really a number. So this is kind of a weird thing as well. So the trick here is to rewrite the expression as a quotient of two things. So there's a lot we can actually do to this limit. So there's a lot going on. So here I'll leave the sine of x alone. But the square root of 1 minus x over the square root of x, that's just the same as the square root of 1 minus x, right? I can break up this square root. Okay, and this thing right here, if you notice, I'll circle it in red, right? So these things are being multiplied together in the numerator. Right, that thing approaches 1 as x approaches 0. So I can think of this limit as the following. Right, times 1 minus x. Right, so I just kind of move this guy over here to the left because they're all being multiplied and the whole thing is being divided by the root x. And if you remember from way back when, right, you can apply a limit law here. I'm going to apply the limit to this thing and then times the limit of that thing. And this is simply because this thing, square root of 1 minus x, is not really giving me any trouble. So I'll go ahead and evaluate this limit. We know that this is equal to 1 by plugging it in. So I'm really just left with, right, the limit as x goes to 0 plus of this thing, right, and then times 1, but that's just, just 1. So we're good. So really all I have to do is evaluate this. And now if I plug that in, we see that we do get sine of 0 over the square root of 0, which is 0 over 0. Okay, so now I have, right, the classic, right, indeterminate form, which means I can do L'Hopital's rule. So we would get, let's see, 0 plus, this would be cosine of x divided by 1 over 2 root x, which is the derivative of root x. And now I'll simplify this, right? So since I'm dividing by a fraction, that's just, I can bring it upstairs. So this is 2 root x cosine of x. And both of these are continuous at 0 plus, so plugging that in, I would get 2 times the square root of 0 times cosine of 0. So that's 2 times 0 times 1, which is 0. So this limit is in fact 0. Okay. So there's a lot of simplification going on there, but this 1 minus x business was just kind of there to scare you. All right, so now the next two examples are kind of the hardest types of indeterminate things. So here, this is a classic limit as well, and we'll see that the answer turns out to be something that is actually kind of a definition of a number in particular. But anyway, if I plug in infinity, again, I hate when I say that, but if as x approaches infinity, rather, right, this thing goes towards 0, right? So inside the parentheses, I will get 1 plus 0, and then this would be infinity. So if I simplify this, it's 1 raised to the infinity power. So this is called an indeterminate power. All right, so you might think, oh, 1 to any power should be 1. Well, it's not really, because what happens if x is 1 here? Well, if I plug 1 in, I would get 1 plus 1, which is 2 to the 1. All right, so that's actually 2 already. So when x is a small number, not even a huge number, right, it's already bigger than 1. So this thing is going somewhere else other than 1. So anytime you have an indeterminate power like this, I want to rewrite this expression. So over here real quick, let's say I have 5 squared. So I know that's 25. But I could also write that as e to the ln of 5 squared. Just because e and ln are inverse functions, right? So those things cancel when I'm left with 5 squared. So I'm going to use this little trick. I'm going to call this e to the ln of 1 plus 1 over x to the x. Okay, so I've applied e and I've applied ln to that expression. Doesn't change a thing. So because e to the x is a continuous function, we can bring this limit up until the exponent. So I'm going to draw e pretty big here, and we're allowed to bring this limit up here. So, and that's just because the only thing that depends on x is the thing inside the exponent. So in order to evaluate this limit, I need to get up into the exponent here. Now, finally, what I really need to do is evaluate this limit in the exponent, but I can use a logarithm law and bring this x down in front. That's because ln of a, right, to the b is equal to b ln of a. So that's a logarithm law from pre-calculus. So we have the limit as x goes to infinity of x ln of 1 plus 1 over x. So in reality, this is the limit that I want to perform right there. So I'm going to take that thing out, and I'm going to come down here and try to do that. And we'll see that whatever limit I get, the answer to the original will be e to whatever that limit is. So we have limit as x goes to infinity of x ln of 1 plus 1 over x. Now, we see that if I plug in, I didn't really leave myself a lot of space here, but if I plug in infinity, I would get infinity times, because x is going towards infinity, ln of 1, which is 0. And so this is an indeterminate product, which is like the previous problem. So in this type, what we want to do is write it as a quotient. So let's say I have 5 times 2 up here. I could actually, if I was crazy, I could write this as 2 over 1 over 5, correct? Multiplying by 5 is the same as dividing by 1/5. So I'm going to use that little algebraic trick here. Since I'm multiplying by x, I'm going to keep the ln the same, just because ln is kind of complicated, right? And I'm going to divide by 1 over x. So multiplying by x is the same as dividing by 1 over x. Now, if I let x go to infinity, I see I get ln of 1, which is 0. And if I let x go to infinity to the bottom, I also get 0. So now, finally, right, I can do L'Hopital's rule. So this is L'Hopital's rule. So x goes to infinity. All right, so I need to do the derivative of the top, which I'll do that in a second, but I definitely know the derivative of the bottom is this. Okay, so what is the derivative? Let's go over here. Let's see, ln of 1 plus 1 over x. The derivative of that. So the derivative of ln of anything is just 1 over that thing, correct? So 1 divided by this stuff. Now I have to multiply by the derivative of the inside. The derivative of 1 is 0, and the derivative of that is negative 1 over x squared. So my derivative of the top thing is 1 over 1 plus 1 over x times negative 1 over x squared. Okay, so this was just me showing you how to do the derivative of the top. Let's continue with this limit. So we have the limit as x goes to infinity. Notice that this is awesome because cancel, the negatives cancel as well, right? So those things are gone. And really what I'm doing is just the limit of 1 over 1 plus 1 over x. And so as x goes to infinity, this part right here goes to 0. And I'm left with 1 over 1, which is 1. So I'm not done, right? So again, this is the, let me try to get this out of the way. This is just the exponent. So now this thing goes back here. E to the 1. So my answer is E. Okay? So that's a pretty crazy problem, but in some textbooks, this limit is actually defined as that number E. So last example, let's try this one. Again, if I try to plug in 0 here, what do I get? Well, tangent of 0 plus, and then to the 0 here. So tangent of, as x approaches 0 from the plus side, we know that tangent goes towards 0. So here I get 0 to the 0. And this is an indeterminate power. Again, you might think, oh, 0 raised to any power should be 0. But then anything raised to the 0 power should be 1, right? So this is kind of battling between 0 and 1. So let's figure out what happens. So again, I would have to do the limit as x goes to 0 plus of e to the ln of tangent of x to the x. Now, none of this part of the problem changes, right? I still bring the limit up here. And I can bring that value down in front. So I have x ln of tangent. Okay? So this is the limit that I truly want to perform. So I'll bring it down here. X ln of tangent. So if I plug in 0, I would get 0 times ln of 0, which is actually negative infinity. So I get a product, again, indeterminate product. So I have to write this, leave the ln thing alone. So I write it as, since I'm multiplying by x, I'll write it as ln of tan over 1 over x. Okay? Now, when I plug this in, I would get negative infinity over infinity, because as x approaches 0, the bottom would go towards infinity, which is indeterminate form as well. So I can do L'Hopital's rule here. So down here, I'll say, okay, what is ln of tangent of x? Prime. So that would be 1 over tangent of x. And then the derivative of tangent is secant squared of x. So up top, I get secant squared of x over tangent, all over negative 1 over x squared. Okay, so let's simplify this thing. What is secant squared over tangent? Well, this would be 1 over tangent would be cosine over sine. And then this is 1 over cosine squared of x. So really I have 1 over sine of x, cosine of x. So this is 1 over cosine of x, sine of x, all over negative 1 over x squared. So writing this in a different way, I can bring the x squared up. So I have negative x squared over cosine of x, sine of x. Which if I plug this in, I get 0 over 0 again. Ugh. Okay? So I have to do L'Hopital's rule again. And I'm running out of space. So here we get the limit as x goes to 0 plus of negative 2x all over. The derivative of this would be, let's see, product rule. So that would be cosine of x times cosine of x plus negative sine of x, sine of x. So I get the limit as x goes to 0 plus of negative 2x all over cosine squared of x minus sine squared of x. So I evaluate the limit here. I would get 0 over 1 minus 0, which is 0 over 1, which is 0. Oh my gosh. Okay, so the limit is 0. I plug that in up here. The answer is 1. Okay, so that was pretty crazy, but you have to use L'Hopital's rule twice. All right.